Great that you're all here. Good to see you. It's a great honor and pleasure to introduce Barbara Terhal. I'm sure you all know her very well, but also want to say a few words. Actually, Barbara Terhal has a very long history in quantum technology. Already in her PhD work, she developed the concept of an entanglement witness as opposed to a Bell inequality test. Then after her PhD, she went to IBM until 2010, when she left IBM to become a professor in theoretical physics at Aachen University, supplemented by a position at Jülich from 2015 to 2022. She has also been a fellow of the American Physical Society since 2007 and a distinguished visiting research chair at the Perimeter Institute since 2014. Since 2017, she's also a professor at QuTech, TU Delft. And Barbara has a long-standing interest and track record in quantum error correction and fault tolerance. She views the scalable implementation of quantum error correction as one of the great challenges in physics today. The fact that this challenge can be viewed both as a question of mere engineering, as well as a question about the fundamental viability of macroscopic quantum information, is precisely what makes it fascinating and thus its resolution groundbreaking. And so I'm hoping to hear all of that in the talk, Fermions, the Final Frontier. Barbara, it's a pleasure. The floor is yours.
Yeah, I will not talk about quantum error correction. And as a theorist, I think I have a slightly harder time than the experimentalists here at QuTech to decide, what my group is doing, or, what is the thing that I want to achieve. Because what I typically do is, I have various projects, sort of one PhD per project. And but today I'd like to talk about something that I find enjoyable and interesting. It's a little bit theoretical, mathematical, computer science oriented, relates to optimization. So it doesn't directly correspond to, any experiments that you are doing or some of you are doing. But maybe it provides a different perspective, and maybe it will have some interest in if we do simulations, like what quantum systems we would like to simulate or understand and so on. And so I'd like to sort of tell you a bit of the story and the motivation. So I'll be very light on sort of, technical results in terms of explaining details. That stress more, the motivation, the why, what, and several open questions actually that we're interested in. Yeah, so and the title that I chose was just popped up in my head, Final Frontier, maybe to lure an audience here to this room. Well, I think fermions are sort of interesting. I find sort of bosons much more acceptable, and fermions kind of weird, although you say, well, okay, you have to, indistinguishable particles, you have two different, it's a very sort of natural thing that comes about, but in other ways it can be strange. And what I'd like to convey in my talk is in what sense maybe they are stranger than qubits, in what sense they are different than qubits from a sort of many-body physics perspective. And and this is sort of, my perspective. There may be other, ways in which you see fermions as very different. And of course, in the lab, you don't have qubits, you have typically fermions and so on. All right, now, technically, this relates to some work we did, and that's on the archive by a postdoc in my group, Heresimenko, Jaroslav, Maarten Stroeks, who's sitting there, and then it's a collaboration with Jonas Helse at QSoft in Amsterdam. And we were also motivated by work by Hastings O'Donnell. And then if you want to know more about sort of work in between what's called operations research, which is a part of computer science math, and quantum information science, you could look at this review. And we're also doing some further work at the moment that I'll come to at the end of my talk. All right, so what I want to start with is just some basic things. And so for some of you, this may be extremely basic, for others not, so it's a little bit hard to judge. But this is the wrong way direction. Yes. So, so qubits versus fermions, very basic things that people have studied and have looked at. So if you have n fermionic modes, I'm just labeling them with some, creation and annihilation operators. And this label I can also include spin or something like that. Now that state space, I can always map that onto the state space of n qubits, of course, right? So in principle, I should be able to map these operators onto some operators acting on qubits. And that's what people have been doing. And sometimes they don't use n qubits, but you use a few more qubits because you want to preserve some properties of sort of the algebra of these operators. Now, and the most well-known mapping that accomplishes the sort of mapping from, these fermion operators to qubit operators is the Jordan-Wigner transformation. And you can concisely, so we will work often with these Majorana operators, yes, instead of the creation annihilation operator, we just define 2n Majorana operators. And it's nice to have some nice properties because, well, some people are interested in Majorana physics, other people just like to use them because they're all anti-commute, and sort of every operator is sort of the same, and they're all squared to the identity and so on. So they're sort of like Pauli's, except they're all anti-commute, basically, right? And that's why you can map them onto Pauli's, but you have to make sure these Pauli's are anti-commute. And this is what the Jordan-Wigner transformation does. But the Jordan-Wigner transformation is just one possible transformation. And there have been a lot of work on mappings to optimize efficiency in the following sense. So for example, you want to maybe, map these n modes on, n qubits, maybe more, but not too many. Secondly, if you have some operators for these things, let's say you have some Coulomb interaction that you express in terms of these operators, it involves only, 2 of these, 4 of these operators, 2 sites, say, or on the same site with a different spin, then you would like to preserve this locality. So you don't want to map it onto Pauli's that act on like gazillions of qubits, right? And you may also want to, preserve geometric locality and so on. Right, so you can ask what's possible there. Now, before I say what's possible and what's known, and some of you may know this, because there was also a PhD student of Stephanie, actually Mark Steudner, who worked on some of these things and developed some of these mappings. Okay, so let's just introduce some terminology that we use. So 2 terms. One is what we call local, or 2 local, 4 local, 6 local, or maybe order n local. So I don't care whether it's 2, 4, 6, but you shouldn't be growing with n with the number of modes. That I call it order 1. So basically, all fermionic Hamiltonians that you're interested in are order 1 local. Say I call, something that is quadratic, I call it 2 local, something that's quartic, I call it 4 local. Okay, so that's just some terminology that we're using. And I can also use this for qubits, where I say, okay, some Hamiltonian that has, is written as sum of terms, and every term acts on, order 1 qubits. I call this a local Hamiltonian. Okay, the other thing is more of a relevant thing, and it turns out that this is where qubits and fermions turn out to be different. Okay, so it's this notion of sparsity. So we call a Hamiltonian Q sparse if each fermionic mode operator appears in at most Q terms in the Hamiltonian. Now, if you have a lattice Hamiltonian like a Hubbard model, it's clear that this fermionic operator, occurs in terms that are just, nearby, and it's very sparse, right? It's order 1 sparse. So lattice models, typically physical models where maybe the system is growing, the lattice is growing, but the number of the number of terms you interact with, the number of terms in which the operator occurs is not growing. Those are called sparse. Yeah? Dense is the opposite of sparse. Now, of course, you can immediately say that sparse things are very physical, right? But people have studied dense models, and this is where, exactly there's some differences. Okay, so now what's known? So this is the old result. Ravi and Kitev worked on this question of this, these mappings. For example, they showed that if you have a qubit Hamiltonian that is order 1 local, but it's not necessarily sparse, then you can map it onto an order log n local qubit Hamiltonian. What that means is that in this qubit Hamiltonian, there will be terms that act on log n polys, as log n qubits, right? Poly terms that act on log n qubits. Now that's sort of, there's sort of a price you pay from going to fermions to qubits. And that price has some, a consequence for quantum simulation, because if you do, if you sort of simulate the fermionic dynamics on your quantum computer or your future quantum computer using qubits, then you will pay a cost which increases, linearly with this poly weight. Because the point is, for example, this is a circuit out of Nielsen and Chuang, with saying, oh, I want to simulate ZZZ. How do I do that? Or maybe, it's not ZZZ, but it's something that is acts on log n qubits. Well, I just sort of have to, do some Clifford circuit that converts ZZZ to a single qubit Z, and then I do that and I invert it again. So the point is there's some extra gates that you need to do in order to do these log and local polys. So there's so that's any, now then you can also ask, and actually we thought this following question was actually resolved. Surprisingly, it wasn't actually, we couldn't find the answer anywhere. This is not something that we published because it's just a small point. But then you can say, oh, well, okay, so let's restrict to sparse models. So, okay, order one local, but now they're also sparse, right? So every Majorana operator only, interacts sits in order one terms, let's say 5 terms, whatever. Yeah. And the system is growing otherwise. So then what you can actually show is you can map it onto order one. So you expect that you could map this onto order one local Hamiltonians, that you don't have to pay this logarithmic cost. But turns out the best construction we know uses not n qubits, but n squared qubits. And maybe there was some discussion, can we reduce this to n log n? So can we get this more efficient? And actually this construction, because this construction, this type of construction is being used for many models, and what people have focused on more is to say, I'm looking at a specific fermionic model like the Hubbard model, or something that I want to simulate, and how can I now minimize the number of qubits and the weight of these, qubit terms for that model. So there's a lot of work on that to optimize it, because that's of immediate interest for quantum simulation to optimize it, right? So we asked a slightly more general questions, and surprisingly, this was actually not known. And one thing to mention actually is that in these mappings, it's a curious connection with error correction that also people have been exploited. Yes.
Sorry, just for my general context.
Yes.
Coulomb Hamiltonian is neither local nor sparse. Is that?
It's local. No, it's 4 local. It's 4 local, like the 4 operators. And sparsity has to do with, well, yeah, the point is it's a little bit, the point is that the interactions are decaying. So the sparsity doesn't say how strong the interactions is. It's a more coarse-grained formulation. So if I keep any interaction as non-zero, it's not sparse, right? But so it's a little bit imprecise there, yeah. All right. Yeah. Is there any other question? Oh, people are good. Yeah. So one thing about these. So what we want to do here is we want to map fermionic operators onto qubits. And the way this is actually done is actually involves a stabilizer code, surprisingly. So there is a way in which these operators that we have to map, which are, this is actually just a side comment, so I put it in small, and if you don't understand it, just ignore. You have these products as Majoranas, you can write all the fermionic operators in terms of products of something like this, which is a vertex operator, X vertex K. This is sort of an edge operator because it involves J and K. You can write these as polys, but then, polys, you are missing some constraints. And then, the product of these edge operators around the loop has to be the identity, and those impose some some constraints on these polys, and these turn out to be like stabilizer checks. In stabilizer code, you have to meet some checks. You're in a subspace, so you have to sort of put yourself in a subspace where these are enforced. But the problem is that these stabilizer checks are not like, you know, the Turing code, the stabilizer checks on 4 qubits. But the code that is underlying it, if you do this naively, is a code where potentially the stabilizer loops are gigantic. And so you have to have a procedure in which you have to make them small. And so this is surprising that this is sort of, you know, actually not completely understood. Yeah, but here so you see that there is a cost when you go from fermions to qubits. It's not like, okay, it's efficient. And then, so this is the point I want to make. Fermionic Hamiltonians are how more powerful. If I go from a fermionic to Hamiltonian to a qubit Hamiltonian, I have to have some overhead in some form, right? But now you can ask, if I go from a qubit Hamiltonian to a fermionic Hamiltonian, do I also have this overhead? Well, the answer is no, otherwise I wouldn't be saying this. And so if you go from a qubit to a fermionic Hamiltonian, it's actually fairly easy, because we say, okay, I have a fermionic mode. And that fermionic mode is these 2 Majoranas. Okay, so there's a whole, you know, this whole algebra, doesn't matter that much. But what we do basically is we take, okay, I have my qubits. Sorry, I'm going to go from qubits to fermions. So I have a qubit, and I replace it by 2 fermionic modes. 2 fermionic modes is 4 Majoranas. So now I just identify, I say, okay, Pauli X, wherever I find Pauli X, I replace it by the product of I C1 C0, Y, I C2 C0, Z, I C3 C0, and then, you know, X, Y, Z is proportional to identity with an I, and that imposes some extra constraints, which I can also just put as part of the Hamiltonian. So this is a very simple mapping. Why is it simple? Is because, okay, I had n qubits. Okay, now I have 2 n fermionic modes, right? And then I just have some additional local constraints. But other than that, and maybe, you know, if I had a Pauli operator which acts on 2 qubits, okay, now it's a Majorana operator that acts on 4. Okay, there's a slight increase, but it's very small. And the other way it wasn't. Yeah. Okay, so these are just hints at that. Yes, yes.
So from my understanding, so you're saying that a local fermionic Hamiltonian is more powerful than qubits, but if you would map, let's say, one fermionic Hamiltonian to another, I imagine there's also some overheads, right? So
There's also some cost.
Also some cost or overhead in doing so, right? So is it?
Yeah, of course. The point is that if you have a free fermion Hamiltonian, you can't map it onto something with interactions. So yeah, within indeed the class of fermionic Hamiltonian, you have different complexity, or some are harder or not. But the powerful is not in terms of that, is because you're saying, well, I mean, maybe I'll come to that in what's, because the question here now is, okay, we have these mappings, okay, so what, you know, maybe is there another way in which this manifests that's more powerful? Because that's basically what we want to ask ourselves. Yes, yeah.
See, so a very intuitive use of fermions is an electron and a double dot, like a charged qubit. So can you describe how the mapping works in that case? It's, I guess there's some raising up.
Like you want to map the fermion to a bunch of qubits. Is that what you're saying?
You want to encode the qubits in a charged qubit.
So you have qubits and you want to encode it into yeah, okay. So you have a qubit Hamiltonian, and well, this is a fairly general mapping, of course, right? And so you could say, okay, I have double dots. That's 2 fermionic modes that can represent 1 qubit. Yes. And there's this particular. You could say, okay, 1, 1, 0 is you know, a qubit in state up. 0, 1 is in down, and the other states.
Right. But,
yeah.
But let's see. So the fermionic operators, how would they be written? It's like the sigma X, for instance, I suppose would be sigma. Sorry, sigma dagger C or CJ, like the raising operator on one side and the lowering operator on the other side. That would be a sigma X operator. Sigma.
Sorry, say it again. Sorry, but you want to know the exact mapping for? Well, yeah, I mean, I can rewrite these in terms of creation and annihilation operators. right? Because then I can write this in terms of a creation thing. But now I've written in Majorana's because it's a little simpler in this language.
Yeah, that's a
Yeah.
I don't, after all these years, still don't have great intuition for my around. Right?
Well, there's a bunch of, it's like the P and the Q in bosons, right? There's like, yeah, well, anyhow.
In which sense do you impose this condition on Majoranas? I mean, is it a limitation on the available space in which they act, or yes?
Yeah, you can, well, okay, so you can put it in the Hamiltonian with a strong term so that the ground space obeys this property. Or you can say, I do dynamics and I start in a subspace in which this is obeyed, and then it will continue to be obeyed. Those are options, yeah. But I think even if you're not working in a subspace where it is obeyed, I think you can preserve the dynamic. So yeah, it's not. It doesn't pose any limitations.
Oh, thank you.
Yeah. Okay. Yeah. Okay. So maybe we'll move to the. Yeah. So okay. So the answer. Okay. So in what sense? Okay. Now these were just fermionic to qubit mappings. They're relevant for doing simulations. Yeah. But I'm interested in optimization problems. Why I'm interested in optimization problems? Well, we can say something about it mathematically. There are long histories of studying optimization problems in classical physics, of course, in quantum physics for ground state energies and so on. And so then the question is, are there any fundamental differences in fermionic optimization problems versus qubit optimization problems versus, classical optimization problems? Now, all these types of problems can be hard, as we know, for classical optimization problems. You have traveling salesmen and these things like the NP complete, the NP hard. Now, such a thing is also true if we ask about determining the ground state energy of a Hamiltonian, not maybe a free fermion Hamiltonian, but something more generic, and there are results on this. And they're called quantum NP hard. What it means is that even a quantum computer couldn't solve this problem, couldn't determine this ground state energy. Now, if you say you have to determine the ground state energy, you also actually have to specify precision. And often these problems, the way they're stated, are actually, you ask for a lot of precision. But then you can also ask, for example, for a typical, quantum system, if I have n fermions or n particles, the energy will scale like some, with n, right? Alpha times n. So you can say, well, okay, maybe I estimate this ground state as beta times n, and alpha minus beta is just small. So what I actually do, I kind of estimate the energy density, so to say. I don't, maybe, if I compare alpha times n times beta minus n, the error is still extensive in n. It grows with n, but is this a good approximation, a bad approximation, right? You could say it's a bad approximation because the absolute error is large. It's a good approximation because I get the density right. So here you see that, the approximation that you ask for is actually relevant. So we don't want to focus on getting the energy exactly right. We want to ask about approximation algorithms. So what's known there? Okay, so now this is sort of the classical story, sort of classics in the classical computation land. And here's an optimization problem that people have looked at a lot. It's very simple. So I have a graph, has some vertices, some edges. Here I have a graph with 5 vertices. And I have to assign for every vertex, I have to assign a value -1 or +1. And the goal of that is to maximize, not minimize in this case, maximize this Hamiltonian. That's to say, what I like to do is that, if 2 vertices are connected, that I like to put them one in plus and the other one in minus. So it's sort of like an anti-ferromagnetic interaction. And this type of problem is called a max cut, because basically I'm trying to partition the set of vertices into 2 sets such that the number of edges and one set gets the +1, the other set gets the -1, and so that the number of edges between them is maximized. Now, so determining the optimal partition between these sets is NP complete. It's a hard problem. And there's also, there's a weighted version where you weigh every edge, doesn't matter so much, but there's a very good strategy. And the point is that the strategy extends also to quantum problems, or that's what the research is about. But the strategy is something that is say, we relax and we round. And the relaxation step is sort of like this, to say, okay, well, we're trying to put every vertex either, assign -1 to +1. But wait, let's now do something else. Let's assign it a little vector that has that just has length 1. Let's say a 3-dimensional block vector could be, but it could also be an n-dimensional vector. And let's replace this sort of by the inner product between these vectors and solve that problem. Turns out that's an easier problem. This is a very common story. If I have sort of constraints that, say my problem can only be integers, then it's hard. Whereas if I, relax it and I can have more a bigger space, it comes easy. So you solve that with these vectors, but then you say, okay, and I got these vectors, but in the end, I want to convert it, and I have to go back to sort of, rounding it. That's this next step to make it integers. Okay, so there's an algorithm for doing that, for this sort of random, what they call randomized rounding, because it uses some randomness. And then this sort of famous result, which is Humans-Williamson, that says that if you do that, so you relax this into terms of optimizing these vectors, you can do that efficiently. You have an algorithm. And then you do this rounding, and then you get a value for this optimum, which is a fraction, a constant fraction of the true optimum. And this fraction is at least this high. That's what's been proven. Yeah, for any graph, for general problem of that type. And now there is also, so what's fascinating, or why people have studied this in computer science, is that it's also known that it's actually hard to get beyond a certain value. So it's hard if you want to get a fraction that's 0.941 or more, there's no algorithm for that. It's NP, it's shown to be NP complete. And and why is this the case? Well, this relates to a famous theorem that's proved in classical computer science, which is called the PCP theorem. And there's one motivation for us to do this kind of work is that there is actually a big luring problem, which is the quantum version of this. But let's leave this aside. What is this? What is this about this PCP theorem? Well, first of all, let's understand this. So when this is hard, it means that there's no classical algorithm that says, oh, I can reach any alpha, like alpha can be 1 minus epsilon. I can go for any epsilon. And that algorithm is efficient. Now, the algorithm may be inefficient in epsilon, but it's efficient in n, right? Because then I say, oh, well, if just pick alpha 0.95, yeah, okay, so maybe there's some overhead, it's a big constant, depending on that 0.95, but otherwise it's efficient algorithm in n. So that's what this states. It says it's not possible. And this non-existence of this algorithm is actually related to this PCP theorem. And let me just say what this PCP theorem is that it's not, the way I'm stating it here is actually not for this max cut, but you have some problem which is just, you're trying to find some bit string and there's some bunch of constraints, right? And you're trying to decide whether there is a bit string that satisfies all the constraints or not, say. Yeah, now that's a problem, could be very hard to decide. But now let me state a much simpler problem, which is either there's a bit string that satisfies all the constraints, or 99% of the constraints are not satisfied. Well, that looks easier, right? It's just like, okay, well, maybe then finding that bits, and I have to determine which is the case. That is the problem I have to solve. Yeah. But there's a much bigger gap between one scenario and the other, so this looks like an easier problem. And what this PCP theorem says is that this problem can sometimes be as hard as a problem of deciding whether, everything is satisfied or not. Maybe one is not satisfied, right? Okay, and so the point is that actually this relates to this estimating energy density. Maybe it's not entirely clear, but, it kind of says that for classical Hamiltonian, even estimating an energy density with some very small error can be hard. For not, not for every Hamiltonian, for some problems this is hard. we don't know whether this is the case quantumly. We don't know how hard this is. Right, so we want to actually understand some of this approximation also to understand this question. Okay, right, okay, so now I hope I haven't lost everybody with this PCP thing, because maybe I'm stacking a lot of things on top of each other, but let's now move to, I haven't talked about fermions that much, but I want to now say, okay, so people have looked at the optimization for classical things. So we can do this the same, for quantum problems. And I'm just going to work in a setting where I'm actually not looking at the ground state energy of a Hamiltonian, but I'm looking at the maximum eigenvalue of a Hamiltonian. Okay, doesn't matter, of course, because I could change h to minus h. And it's just to mimic this situation with max cut, which I look at the maximum, I want to maximize value. And so then what I ask for is an efficient algorithm to give me a state, so that gives me some constant times this maximum eigenvalue, right? That was sort of what we had for this optimal max cut. We said this Hummans-Williams algorithm gives me 0.87 of the optimal value. But then I have to say, well, okay, there could be a classical algorithm, could be a quantum algorithm. We actually know very little about quantum algorithms in this setting. But the other thing is to say, well, what does this algorithm do? Does it give me a state as output? But maybe it's a classical algorithm. I can't even describe the state, right? So, there's several things. So let's say we just give, we want to have some algorithm that gives you that there is a state which has at least this energy, So, but this, but if we want a classical algorithm, we have to sort of, we may expect that we like to represent these states that we, try to find, we like to represent them efficiently, right? Because typical states will not be, like the ground state may not be efficiently represented. So that's an extra layer of difficulty that we have quantumly. Right, so we can say, well, okay, maybe we can just restrict ourselves to subclasses of states and see if we can get a constant approximation ratio for those. Okay, so what I mean by constant approximation ratio is that this maximal energy is some lambda max, and the state achieves some, fraction of that lambda max. Now, of course, you could also say, well, what does it mean physically? Is this anywhere close to the ground state? Does it have the same, expectation values of operators? I honestly don't know. So that's a weak point in terms of how it connects to physics. All right, but okay, so you can enhance this question, say, okay, maybe I don't care about efficiently representable, maybe there are states on the quantum computer that I can look for. All right, so now there's a very old result, and there are many more results, but by Leap 73, that says that if you just look at product states, obvious choice, right? These are easy to present. Then for every Hamiltonian, then there's a product state that at least achieves a 1/9 of the maximal energy. Okay, and you can generalize this a little bit. It doesn't actually say that you can easily find it. And there is actually an algorithm, if you have to find it, write down a general algorithm that finds it, you actually lose this constant approximation in general ways. Okay, so but now now I come to sort of the motivation. Now let's talk about fermions. Okay, so you could say, is there such a leap theory for fermions? Right, that's kind of the question. So what are the product states that we want to look at for fermions? Well, in very natural class are states which are sometimes referred to as single Slater determined states, and I think you're all familiar with them. You got the vacuum, you got K particles, you put them, you fill up the levels, right? In terms of you put them in K different orbitals. And these are the eigenstates of free fermion, non-interacting fermion Hamiltonians. Now you can generalize this class a little bit in allowing so-called Bogoliubov transformations, in which you can also include things like a BCS superconducting state, which is not a state with fixed fermion number, right? Because the state of having 2 electrons, 4 electrons, 6 electrons, and so on. And these are called Gaussian states in general. But okay, so let's not, we don't have to go into that. But the point is, these states have a very efficient description. You just give the orbitals that are filled, for example, or you can give the correlation matrix. Yeah, so these fulfilled, you can say, okay, now I can ask fermionic Hamiltonians, do I always get a constant approximation ratio if I optimize over those states? Right, like this 9th of leap. Okay, sounds like the answer. All right, so I worked on this during Corona time, right? So we were in Corona, I'm sitting at home, I heard a talk on this leap theorem, I say, hey, good question, it's an open question, nobody's proved this. So let me try to prove this, because it seems like that's try to extend this, the tools that they had for qubits to this fermionic case. Because this proof of leap was actually fairly simple. So is there a Gaussian state such that for every order 1 local fermionic Hamiltonian, think about the typical Hamiltonians that you know, but maybe they're dense, such that there is a Gaussian state such that you achieve some constant fraction of this maximum energy. Didn't seem to work. So, I was kind of stuck, didn't solve the problem. And then, of course, it turned out to be not true, as happens often in mathematics. If something doesn't work, it's just not true. So they had a very nice result. And they showed that actually there is a class of Hamiltonians. I'll come to the definition in a moment. These are SYK Hamiltonians, such that YKTF. They are fermionic Hamiltonians. They have some randomness. It's a class of Hamiltonians, meaning that you have to draw parameters from some Gaussian distribution, and you get one model, draw again, you get another model. So you have to say, okay, with high probability, some property is true. So this with high probability, they showed that for all Gaussian states, this ratio is decreasing in n. It scales like 1 over the square root of n. So this is weird, basically. You would say, I don't know, would this be surprising? It's maybe people would have conjectured this, but the proof of this is fairly non-trivial. And it kind of says that this ground state of this model, they are like deeply entangled. So this model is a sort of an all-to-all connectivity. And you would think that, if you have qubits, you have all-to-all connectivity, then it's like mean field works very well, right? And everybody may as well by themselves, because I can't be entangled with that person and that person, that person. So I'm just in my product state. I mean, that's the sort of, anthropomorphic version of the mean field idea that product states work very well for models with very high connectivity. But the fact is, this is not true for fermions. This is what this theorem shows. It's like fermions have a different limit, that if you have very high connectivity, these Gaussian states, they fail miserably, because this, well, at least in this quantitative sense. And so the ground is somehow deeply entangled. And so then another open question that we've heard rumors that somebody solved this, can this ratio be worse? Are there models for which this is like, even much worse? Well, we believe for these types of Hamiltonians, which are 4 local, we can't make it worse, but I haven't seen the proof of this. Okay, so what's this SYK model? And maybe you've heard rumors about this has something to do with gravity, has a gravity dual and so on. I don't understand this at all. And I'm not so interested in those aspects because I don't understand it. Maybe other people are. People are interested in simulated dynamics of this model. But then, this is a dense model. And actually, if you have to simulate the dynamics on the quantum computer, you get this log n factor that we didn't like, right? So there is this cost that you have to pay in terms of, the dynamical simulation. Okay, but what's the model? It's a Hamiltonian, and we write it in terms of Majoranas. Every term is a product of 4 Majoranas. And you can take any set of 4 Majoranas, and then you multiply it by a constant. And this constant is where the randomness comes in. This is just a chosen Gaussian random variable. So you pick it, and it has its mean 0, and it's just some standard deviation. And there's some normalization. Yeah, so it's and so this model, was introduced also to study, the spectrum, partition functions, and it believed to behave chaotically. Actually, like a big nucleus, they say like a compound nucleus. Sorry, this is not a big nucleus, it should be, okay. But the point is, it's sort of like the models that try to, maybe you know about random matrix theory. You have random Hamiltonians, have a certain spectrum, and you can say, okay, for this is sort of modeling, you know, in some sense a random Hamiltonian. You can look at its spectrum or density of states. All right, now another open question is that, can you get behavior like this 1/√of n, you know, non-constant fraction when the model is non-random? Because the techniques for proving this, you very much use this randomness. Another interesting fact about this model that was proved in this paper is that, so these Gaussian states that you can efficiently present, they are not good approximations of this ground state. But they showed an efficient quantum algorithm that would create a state that has the same energy scaling as the true ground state. So that's an interesting fact, because that says that, hey, maybe for these models, you know, if we really want to create states that have this constant approximation, we need a quantum computer. So this is also sort of the interesting, are these models in which, you know, they lead to problems for which we need a quantum computer? All right, now, given that this question was answered, we said, okay, this is a very dense model. Now, can we then still prove this sort of leaps result if we restrict the sparse fermionic Hamiltonians? Let me remind you, for sparse fermionic Hamiltonians, every fermionic operator sits in order 1 terms, right? So much more restricted. So is there then a classical algorithm which efficiently gives the Gaussian state, which has this constant approximation ratio? Now, you could say, oh yeah, the answer is probably yes. Well, that's what I would think, but then of course to prove this is a different thing. And that's where we, we worked on for a bit. And then we have some extensions and so on. And that all made us understand, much more sort of clearly what could be done. So I'm actually glossing over this whole technical part, but just that's the work that we actually did. And there was some follow-up work which tightened this. All right, now to finish, I have a few minutes or something, I guess, right? Because it's like 10 minutes questions or so, yeah.
That's fine.
Yeah. Okay, so now just a slight difference about what we're doing right now. So I think we want to understand better what makes this SYK model tick for this ground state thing. Is there a non-random model? Okay, so I need some denseness, but can I define some simpler models in which they have denseness, but I still have a constant approximation ratio? And maybe can I, like there's been some results in qubits, can I kind of, transplant them to the fermionic setting? And in particular, can I generalize? So for the classical optimization problems, I showed you this max cut strategy. We say, okay, what I do is I relax the problem and then I have to round it back to an actual solution I'm interested in. And that's been done a bit for qubit Hamiltonians, but not so much for fermionic Hamiltonians. So this is what we want to explore, because what we want is we want to take a problem that's kind of like a fermionic version of max cut. Then we want to say, okay, we relax it. And then from that relaxation, we somehow want to get a good constant approximation factor. Can we work this through? And the model that we study is, we call it fermionic max cut for now. It's a little bit contrived, and I'm not sort of, but again, it's some graph, and it's not the Hubbard model, but at least it has a kinetic energy which is negative and sort of a potential energy which is positive, and there has a specific, relative strength of sort of a Coulomb interaction. You could read like this. Because I have just fermionic modes on a graph, and if there's an edge between two fermionic modes, I have a Coulomb interaction, but I also have the potential to hop from here to there. And then I have some, chemical potential also, which is fine-tuned. So it's a model which has more structure than maybe Deckelbaum model, but we look at that because for this we could do some analysis, and maybe if we have insights we can generalize. Yeah, and so there's a sort of qubit versions of this which use ferromagnetic interactions, which we try to generalize. And now this is a whole slide full of stuff, but actually the point is that the point I want to make is that there are actually known connections with work, in the 50s, like for fermionic optimization and also optimization for qubit states is not a new problem, right? This is very old. Okay, so, and also this idea of relaxation is actually not at all new. It's something that is also being studied. Okay, so let me explain to you how you can view this. Okay, so what I want, in my Hamiltonian, I have terms like this, right? So I want to take a density matrix and I want to optimize sort of linear combinations of these. But the constraints, of course, is that rho should be a density matrix, should be a physical state. So now what we do is we actually, so this relaxation that we're actually doing is that we don't optimize over, a general density matrix rho, which is a positive semi-definite. But we kind of optimize over reduced density matrices, or this is one way of looking at it, of, which are called 1 and 2 RDMs. That should be mutually consistent, but maybe there's not a global state that actually is the joint state of all these reduced density matrices. All right, so you imagine you can have, if you optimize a qubit Hamiltonian, you can say, well, I optimize this term, I optimize that term, make sure if they density matrix overlap, they have the same reduced density matrix. But that looks like an easy problem. But then maybe there's not a global state that is consistent with all these reduced density matrices. And that in physics is called the M representability problem, because what you want to say, oh, I want to have some conditions that say whether this subset of reduced and this set of reduced density matrices is consistent with a global state, with a real physical state. And people have tried to derive these conditions and say, oh, we need to solve this. And once we have all these conditions, then we can just, this very hard optimization problem, we can just completely solve it. Now, I think this is unlikely to completely solve it, but you can still look at what constraints you have, and basically this semi-definite program that you're running, you can run small version, larger version, and that basically gives you more constraints. Okay, maybe this is a bit of a mouthful of things. But the point is that in physics, people have looked at these types of constraints, and we're trying to see if the constraints that we derive connect to that and understand that a bit. But then what we also want to do is that given that you have this, these unphysical, what we call pseudo density matrices that are reduced density matrices, but there's maybe not a global constraint, a global state that there are the reduced density matrix of, those pseudo density matrices you could still try to use to construct actual physical solution. And that's the sort of rounding step, right? And that's what's done in classical optimization. And that's not been so far, at least what I can see, not so much done for these quantum problems. Yeah, and also there was some recent result in which they actually used these, I would say, pseudo-density matrices to construct a quantum circuit to run that would lead to a good approximation. Right, so that's another way in which this can go. All right, so I want to just wrap up. Okay, so I don't know whether my talk covered Fermions, the final frontier, whether it was, exciting enough in terms of okay, so the idea is that fermions have some different properties than qubits, and we're trying to see whether that's interesting, fundamentally interesting as applications for quantum computers or not. Yeah, and so basically that's our motivation, and I hope to have conveyed some of that in my talk here. Okay.
Very good. There were already some questions along the way. Are there any other questions? Anton.
What about bosons? I mean, so there's the usual boson sampling thing, but is there something? So it is clear that fermions in some problems are more interesting than qubits because of the complexity of the approximation. But how would the bosons be placed in?
Yeah. Well, the problem with bosons, of course, is that they're a bit incomparable to qubits, because this Hilbert space is very large, right? And then if you make it finite, there are just few bits, and so that's. But I mean, you're referring to boson sampling and so on. That of course. Yeah. Okay. So you can ask whether is approximation. Okay, so it's good. You can ask the same question: can I approximate the ground state with constant approximation factor by Gaussian states, for example? But I would expect Yeah, I don't know, wouldn't expect this to be true. Why not? Yeah, I don't know, it's a good question, but I'm a bit worried that this infinite Hilbert space may give some annoying technical problems.
So then bosons are an even more final frontier.
Fine.
Well, no, okay, that's just, well, why, because I don't know, because the Hilbert space, because the Hilbert space is infinite, but it's kind of an artifact, right? Because, you never have infinite energy states.
Yeah,
So it's just like, we just have a formalism that, yeah.
all right.
Christian.
Yeah, no, I just wanted to ask on the on this SYK model you showed or discussed that you cannot find this efficient classical algorithm, and then you had sort of an addendum that kind of said that makes it interesting for a quantum computer to solve it, because if it's classically hard and quantum easy, right, then it's something that we hope we can run on a quantum computer, right? But do we have any, or do we know whether it's actually easy on a quantum computer?
Yeah, so okay, so maybe more precise. So what they do in the paper is they show that there is a quantum algorithms, explicitly a procedure that you run on a quantum computer that outputs a state which is guaranteed to have this constant fraction of the total energy.
Okay.
And that is sort of given the model.
Yes.
So then you say, well, let's say I want to do experiments on the ground state of my SYK model. Now, I first want to prepare this ground state, or let me approximate my Gaussian state. Then you say, well, who knows how bad or good this is. Then you get to your quantum computer and say, oh, okay, let me try to run this algorithm, and then I do some experiments. So that's potentially, but it's actually an open, yeah.
But how? What is the scaling of that quantum algorithm then? Is that then?
Yeah, that is efficient. It is a polynomial time algorithm. Yes, yeah. It's a preparation procedure. But the thing is, it's actually an open question. They posed it as an open question whether there is an efficient classical algorithm for some other state. It doesn't need to be a Gaussian state. So they don't know this fully. Yeah.
So the Max-cut problem you're referring to is remarkably close to just an electron in a quantum dot array, and then you can either use the charge or just a spin. Have you considered, let's say, what kind of quantum dot array would it take to solve a Max-cut problem?
Okay, so this is connected subject where you say I take my classical optimization problem and I try to solve it by a quantum means, by some embedding, and the problem I see with, it's of course many people do this, right, with this quantum approximate optimization, but there's very few rigorous results there to show how well you do, or whether you can get show any like guarantee for how close you are to the ground state, or whether you get a constant fraction is so the point is it doesn't seem to fit very, like we have phase estimation, but it doesn't seem to fit very well. So technically it's hard to make, you can still do it, right? But it's technically not so easy to show properties of how well it does. Yeah, that's the that's maybe the right answer here. Thanks. Yeah.
Sorry. Yeah.
No.
Yeah, so you compare the Gaussian state between boson and fermion, and you look at the file of the eigenvalue. But
The what? Sorry, I couldn't hear.
yeah. So in this,
I only did fermions here, and there were sort of Gaussian states, but they're like, free fermion states, or
but there are also like all the efficiency that can be represented. For example, denser networks, right?
Yes.
So would you expect that there would be different?
Yeah. Very good question, because Gaussian states or product states are fairly, restricted, and it would be interesting. Also, stabilizer states would be candidates, because or states with you get from a low depth circuit. So I would say for the SYK model, we would like to know a little bit more what states also don't have a constant approximation ratio. Like, extend the results, negative results beyond Gaussian states. But the point is indeed, like also what I said to Menno, there is the realm of, you know, numerics, because, well, the problem is doing mathematical research is that you make the problem so, you know, want to solve the problem, so you make it into such a simple problem that it has no direct applications, right? So, and if you don't do that, you run into numerics and, you know, conjectures and maybe and so on. So that's a little bit the problem there. If I start working with matrix product states, how do I optimize? How do I prove anything, right? So this gets harder to say something. But I think stabilizer states is interesting. And also for the qubit setting, I'm not sure there are any results there. So.
If there are no further questions, then let's give Barbara another big round of applause.